Quantum computing sounds like science fiction. Computers that exist in multiple states at once, particles that vanish and reappear on the other side of a wall, and machines that could break the encryption protecting the entire internet. But none of this is fiction. It's physics. Over the next 10 minutes, we'll walk through 8 of the most mind-bending ideas in quantum computing, from superposition and entanglement to real machines being built right now by Google and Microsoft that are already outperforming the world's best supercomputers. By the end, you'll understand not just what makes quantum computers strange, but why that strangeness is exactly what makes them powerful. Every classical computer, from your phone to the world's biggest data center, runs on bits, tiny switches that are either 0 or 1. That's it, 2 states, no in between. A qubit breaks that rule. Thanks to a property called superposition, a qubit can be 0, 1, or a mathematical combination of both at the same time. It's not that we don't know which one it is. It genuinely exists as both, until the moment we measure it. Think of a spinning coin. While it's spinning, it isn't heads or tails. It's some blend of both possibilities. Only when it lands, when we measure it, does it collapse into one definite state. That single idea, existing in multiple states at once, is the seed that all quantum computing power grows from. Here's where it gets mind-blowing. 1 qubit gives you 2 possible states. 2 qubits give you 4. 3 give you 8. The number of states doubles with every qubit you add. It grows exponentially, as 2 to the power of n. That might not sound dramatic until you scale it up. Just 300 qubits in superposition together can represent more simultaneous states than there are atoms in the entire observable universe. A classical computer would need to check those possibilities one at a time. A quantum computer can, in a sense, explore vast numbers of them simultaneously. That's not a bigger calculator. It's a fundamentally different way of computing. And it's why even modest quantum machines can tackle problems that would take classical supercomputers longer than the age of the universe. Now add a second strange ingredient: entanglement. When 2 qubits become entangled, their fates are linked. Measuring one instantly tells you something about the other, no matter how far apart they are. Separate them by a room, a continent, or in principle much further, and the connection holds. Einstein famously distrusted this idea. He called it spooky action at a distance, because it seemed to break the speed limit of the universe. It doesn't. No information actually travels faster than light, but the correlation itself is real and has been confirmed in lab after lab. Entanglement is what lets quantum computers link qubits into one interconnected system, so that operating on one part of the system can affect the whole, enabling calculations classical bits simply cannot perform. The third mind-bending idea is quantum tunneling. In the everyday world, if you roll a ball at a hill that's too steep, it rolls back down. It doesn't have enough energy to get over. Quantum particles cheat. They can pass straight through an energy barrier they shouldn't classically be able to cross, essentially appearing on the other side without ever going over the top. It sounds like a magic trick, but it's measurable physics. And it's not just theoretical. Tunneling is already at work inside the flash memory in your phone and the tunnel diodes in modern electronics. In quantum computing, engineers have to manage this effect carefully because the very same tunneling that powers useful chips can also let qubits leak information if it isn't controlled. Here's the idea that keeps cryptographers up at night. Much of the encryption protecting your bank account, your messages, and the entire internet relies on the fact that factoring very large numbers is practically impossible for classical computers. It would take longer than the age of the universe. In 1994, mathematician Peter Shor showed that a sufficiently powerful quantum computer could factor those same numbers in a fraction of the time by using superposition to test many factors simultaneously. Today's quantum computers aren't yet large or stable enough to break real-world encryption, but governments and companies are already preparing for what's nicknamed Q-Day, the day quantum machines catch up, by rolling out new quantum-resistant encryption standards ahead of time. This isn't just theory anymore. In December 2024, Google's Willow chip hit a milestone researchers had chased for almost 30 years, below threshold error correction, meaning that adding more qubits actually reduced errors instead of adding more noise. Willow then ran a benchmark task in about 5 minutes that would take today's fastest classical supercomputer roughly 10 septillion years, far longer than the universe has existed. Then, in late 2025, Google pushed further with an algorithm called quantum echoes, demonstrating a verifiable quantum advantage on a real molecular simulation, running about 13,000 times faster than classical supercomputers, with results other scientists could independently confirm. Quantum computing has officially moved from someday to right now. Scaling these machines up is one of the biggest engineering challenges in the world, which is why Microsoft's February 2025 announcement turned heads. Their Majorana 1 chip uses a completely different approach called topological qubits, engineered to be inherently more stable and resistant to the errors that plague other designs. The real headline is scale. Microsoft says the architecture is theoretically capable of fitting 1 million qubits onto a single chip. For comparison, today's leading machines run in the low hundreds of qubits. If topological qubits deliver on that promise, it could be the shortcut the industry needs to leap from today's noisy, error-prone machines to the large, stable quantum computers capable of truly transformative calculations. So, if quantum computers are this powerful, why don't we all have one yet? Because qubits are extraordinarily fragile. The same sensitivity that lets them hold superposition and entanglement also means the slightest vibration, stray heat, or electromagnetic noise can destroy their quantum state, a process called decoherence. That's why quantum chips are cooled to temperatures colder than outer space, just a fraction of a degree above absolute zero. And because individual qubits are so error-prone, building one reliable logical qubit currently takes hundreds of physical qubits working together for error correction. Engineering around this fragility, keeping quantum states alive long enough to compute something useful, is quite possibly the hardest technical problem humanity is working on right now. So where does all of this lead? Beyond breaking codes, quantum computers are expected to transform drug discovery by simulating molecules atom by atom, design new materials and batteries, optimize everything from flight schedules to financial portfolios, and push machine learning into territory classical computers can't reach. Most experts still put widespread commercial impact in the early 2030s, but the pace of the last 2 years suggests that timeline keeps getting pulled forward. We're watching a technology move from physics curiosity to working machine in real time. And that's the most mind-blowing part of all. This isn't science fiction anymore. It's happening on lab benches right now, one impossible-sounding qubit at a time.